Darn it. There we go. Well, looks like I've been talking for 7 seconds. I'll have to take a video of that sometimes just to show you how confusing it is when I do the screen capture recording. It just sends me a wacky message. So what I want to do today, this is video 29. This is actually going to be more on matrices. So I hope you don't get frustrated with me on this because you might be thinking, come on, Darbro, man, this is not a linear algebra class. This is a statistics class. This is a regression class. Well, I guess you just got to trust me on it. Matrices play a huge role in regression. So I want to look at a couple of things today. One thing we want to look at is called linear independence. And then we also want to talk about the rank. And then what I've, I think in the previous video, this is the bad part about not keeping good notes. I'm pretty sure in the previous video, which actually I posted a couple of days ago, we examined this product matrix, if you will, here where we take x transpose times x, and remember x is the design matrix. And that doesn't really mean much to you yet, but it certainly will. Video 30, it will be the end of matrices in isolation of regression. Well, it's really not isolation of regression, obviously, because I'm bouncing it off this. But a matrix that plays an important role is the inverse of this matrix. And we're going to ultimately today, video 29, is going to be about setting up the stage for this. It turns out that we calculate the coefficients of our model using this in conjunction with some other matrices, which are actually much simpler. So that's kind of why we put so much emphasis on this. Now, let me tell you one thing. Today is, I'm actually recording this, I think June June something. Maybe June 12th, I think it is. And it's kind of hot in Kentucky. Long story short, my air conditioning went out last night. The way my timing usually goes is my air conditioning man will probably call as soon as I get, into this video with you guys. So if he calls, I certainly don't want to miss that phone call. You know how temperamental those folks are. If he calls, I'm going to actually put you on hold. I wish there was a way that I could just pause the video, but there's not. So bear with me. I'm sure it'll be a short phone call. All right, guys. In our last video, we talked a little bit about the inverse of a matrix. And let's just say our matrix is A. And of course we know that the inverse is denoted by A with a -1. And we know that the inverse is that special matrix that when multiplied times our matrix A, that gives us the identity matrix. So in a 2x2 case, the identity matrix is, I'm pretty sure we talked about this before. It's just the matrix that has ones on the on the diagonal. Now let's actually look at a matrix here, and let's say we have 1, 5, 9, 2, 10, 18. No, I don't know. 3, 7, 11, and 4, 8, 12. Now, at this stage of the game, what I want you to think about is we can consider matrix A to be made up from column vectors. And in this case, we can think of this being constructed as four column vectors. So we could call, just for lack of imagination here, we could call C1 159, and we could call column 2 obviously 21018, and so on. Okay. Now, guys, I've constructed this in a special way because I want you to focus on column 1 and column 2. And what you'll notice there is if we take column 1, which is 159, column 2 is 21018, it's easy to see that we could take this column right here, multiply by 2, and create this column right here. So in other words, we could take 2 times 159 and get 21018, which expresses 2 times column 1 is column 2. Now that doesn't seem like a big deal in isolation of other things, but in statistics and even in the theory of matrices, it gives us problems. So what we have here is we have what's called linear dependence. Because we have one column which can be expressed as a linear combination, if you will, of the other one. Now, statistics, when we violate the independence assumption, we got problems. We got major problems. And what happens here is essentially we've got a column number 2 that's really demonstrating the same information as column 1. And again, that can drive us crazy. We'll eventually get into something called multicollinearity, and it's essentially kind of a result of this. So let's just say let's put this in. So we have when one vector, column vector, and actually it works for rows too. When one column vector can be expressed as a linear combination of another vector, again column vector in our case, then this leads to linear dependence. And linear dependence is bad. Okay. Now, let's go. I'll tell you what. Let's get a little bit more theoretical, if you will. I think I should probably do this before going on. So let's say that we have a matrix A which consists of column vectors C1, C2, C3, up to Cn. So, guys, vector A is an M by N matrix, M columns. I'm sorry, M rows and N columns. And let's and we have scalars. K1, K2, up to Kn. And it's important that we understand not all can be 0. Some can be 0, but not all. Can be found such that K1C1 plus K2C2 plus KNCN equal to 0 indicates linear dependence. And linear dependence, again, is bad. Okay, so what we have here essentially is we have 2 times column 1 minus 1 times column 2 plus 0 times column 3. I think. Let me go back and make sure I'm just making this stuff up. So our matrix was, so we have, yeah, sorry, plus 0 times column 4 is clearly going to be 0 because of this right here. So again, notice that some of the KIs, if you will, can be 0, but all of these can't be 0. Well, guys, again, you know, it is what it is when we get a matrix. But in terms of many of the things that we want to do, this would be bad. All right. Now let's go on to regression. Well, no, well, yeah, no. Let's look at the rank of a matrix. The definition of a rank of a matrix, as I see it, it's the maximum number of linearly, it's hard to say, linearly independent columns in our matrix. So guys, this is really not that crazy, considering our matrix A, which was oh gosh, I wrote it down somewhere here. 1, 5, 9, 2, 10, 18. Oh, darn it, darn it, darn it. And we have, what in the world is going on here? I don't want to do that. Wow. This thing's gone nuts. So 7, 8, and 10, 11, 12. Now, if you examine, if we can kind of ignore this right here, we have column 1, column 2, column 3. well, I mean, we can't ignore it, but in terms of the rank, we can ignore it. And we can see that neither of these can be expressed as the other in terms of multiplying by some scalar. For example, to go from here to here, we would have to multiply 1 by 3. When we multiply 5 by 3, we don't get this. We'd have to multiply 1 by 4. When we multiply 5 by 4, we don't get this. So, guys, for this matrix, we can say that our rank is 3 because of column 1, column 3, and column 4. So we don't throw the baby out the bathwater here just because this column right here is linearly dependent with column 2. We still can use it in a rank because it's not linearly. It's linearly independent with the columns 3 and 4. You could also see that column 2, column 3, and column 4 would also be linearly independent. It's still, giving us that our rank is equal to 3. Now, the only reason I kind of take up your time for all this is for the following fact. And I'll tell you what I'm going to do. I have resized my screen, and I'm not smart enough to figure out how to unsize it. So I'm going to start out with a clean slate here. Okay, so important fact. Again, this is all about trying to find the inverse. And again, the focus of today's lecture in the end is how do we find this matrix? Because it's super duper duper important. All right. So there's a fact, and the fact is the inverse of a matrix. And we'll talk about a square matrix, let's say an R by R, only exists if the rank of the matrix is R. So, in other words, we need columns that give us linear independence. All right, gang. Let's look at this, say, in general. So let's let we're going to look at the simplest case of a square matrix. Well, I don't guess it's the simplest. I guess simplest would be a 1 by 1. Daggone it! Why does it do that? I'll fix you. I'll just keep starting over. You know what's going to happen? Probably the last video, I'm actually going to figure out how to do that. So let's let A be. Actually, I want to write a little bit bigger anyway, so that works for me. And let's focus on how we would find A inverse. Now it's really, really easy to do with R. It's even easy to do with the TI-83, 84 calculator. I'm sure the 89, I just don't know it as well. But guys, one of the things we're going to need to talk about here is the determinant. I think I spelled that right? Okay. So the determinant of this matrix, and we'll let the determinant be capital D, is just AD minus CB. And I'm sure all of you know this. Okay, now an important fact. If our determinant is equal to 0, then inverse does not exist. So for our calculations, we have to kind of assume that we do not have a determinant equal to 0 when we're calculating the A inverse. So guys, at the end of the day, because A times A inverse is equal to the identity matrix, what we're looking for here is we're looking for a matrix that I'll call EFGH, which gives us this. Now I'm just going to kind of get the ball rolling here. So what we need is we need a linear combination of AB, EG. So we need AE plus BG equal 1. We also need, for this term right here, we need the second row, first column. So we need CE plus DG equal to 0. We've already done this one. So looking at this, we need the first row, second column. So we need AF plus BH equal to 0. And focusing on this entry right here, second row, second column, we need CF plus DH equal to 1. So guys, we're going to, I don't think I'm going to solve it. I'm just going to kind of give you the, instead of forcing you to go through kind of the drum roll, please, I'm going to give you the answer. Well, guys, using this, it turns out that we can easily find the inverse. I'm going to write really big because there's a lot going on here. By taking D over D, negative B over D, negative C over D, and A over D. Okay, and we can check that. I'm not going to go through the calculations of that, but I always just remember A, negative D. I don't know. So that's what we'll use for the inverse of a 2 by 2 matrix. Now, again, guys, ultimately we're wanting to use all this to find the inverse of X transpose X. And if you recall from last time, this is, a rather simple looking creature. And I don't think there's going to be any misunderstanding here. But guys, remember, in the general case, x sub I squared is not the same as this. Now, I had some pretty clever 3,500 students last semester who I really couldn't understand why they were getting some of the stuff they were getting, and it drove me absolutely completely crazy. In fact, my brightest student, to be honest with you, and he was making that mistake. So just make sure if that's just clear to you. Well, good for you. All right. So guys, the determinant here would be obviously n times some xi squared minus some xi. There we go again. I don't know if you guys see that or not, but what happens on my iPad is I resize things and it annoys me. So guys, what we have now is n times the sum of xi squared. You guys, obviously the summations are from I equal 1 to n, because x's, our x's that we're examining here are just the x coordinates of the data that we've collected. And here we get that. Now, I want to play a little trickery here. And I don't think that anybody's going to have any problem with that part. And the beauty of that is we can re-express this as something that's really, really cool. Now, I don't think we've talked about it. I know we've talked about this term a lot. It's come up a lot. I don't think we've actually given it a name, but we soon will. Okay, so guys, let's go on with the calculations. And let me wrap my mind around what we're doing here. Okay, so what I want to do here is I want to examine this. And using the fact that we know that A inverse and I'm going to just put this the way I always remember it. Which is like this. All right, we've got some work to do here, aren't we? Okay. All right, I'll tell you what I'm going to do. I want this whole space here. Trying to look ahead and see what we're going to get. So I want to create a big matrix here. Now, first, if we take our D term, we obviously know that that's sum of the xi squares over the determinant. And then the two terms here are going to be obvious. And I probably should just write capital D, but I want you guys to have a clear visual of what we get here. So n times xi minus x bar squared. And of course, our A was just the sum of our ones. Now this may be cheating a little bit using this whole A inverses, small d over capital D for this term, and whatever. we can all get over that. All right, gang. So I'd like to get a better expression here. It turns out we can. Let's see. So we know this. We know that the sum we know that x bar is the sum of xi's over n. So this gives us that the sum of the x sub i's can be found by taking nx bar, which would be really, really easy to find. And I think we've looked at this before, that the sum of our x sub i's minus x bars quantity squared can be expressed as minus n times x bar. Let's see. I know that's true, but I'm just having a hard time. Okay, xi squared, sum those up. Yeah. Okay. So we know these two things are equivalent to this statement in this statement. Well, so all right. Guys, losing my train of thought here. So what's actually going to happen here is this first term is going to be, so we've got the first term is actually just going to be 1 over n plus x bar squared, which would be easy to find. Sum x sub I minus x bar squared. And the next term, this term right here, because of this connection right here. Okay. So that's just going to be the sample mean squared okay, and obviously we're going to get the same thing, right? Yeah, for this term we still got this business going on right here. That looks like a lambda, doesn't it? Why the hell Darbo bringing in a lambda? All right, and the other term, let's examine it. This down here, well, that's going to be easy. So really, that's going to be really that's simplified as far as we need to take it. So guys, you can see here that, if you went ahead and calculated the sum of the deviations, from x minus the mean of x quantity squared, the rest of the calculations are really easy to find. I mean, we can clearly find, for example, the sample mean and square it. And clearly we can take the sample mean, square it, and look at the at that times -1. And, and this part's kind of a duh. And so it'd be easy to find the inverse of this matrix if we were given our data, x1, y1, x2, y2, and so on and so forth. So I want to leave you with that. Again, this is, the reason I spent nearly, I'm not really sure, maybe, I'll tell you what, if I've got some extra time, we'll get into 34 minutes. I'll tell you what, I kept you late last video, so for about 10 minutes. I think I'm going to let you out about 10 minutes early on this one. So Guys, again, this is a super duper duper important product here in the inverse plays. And that's not a factorial, that's just a really excited statistical expression, okay? And I better get rid of that. I can see somebody saying, why is Darbo taking the factorial? So no, it just turns out that it's an extremely important matrix that we run into, well, a product that in an inverse that we run into in regression, as I will demonstrate to you in the next video. So guys, have a good one. So let's go UK. Go Cats. See you later.